let me, before we start the lecture, let us look at that quiz question that we had put last time. Remember, the question was that I have a uniaxial medium and a wave is propagating in some direction. The unit vector to that direction is given. So, remember that the d vector is always perpendicular to the k vector, and if it is an extraordinary wave, the k vector and the d vector lie in the plane containing k, z and the optic axis and the d vector. So, this d vector is lying in the plane containing the optic axis and the k vector, and once I know d, I can this angle. So, this angle is equal to this angle, and once I know d, then I can actually calculate the orientation of the E vector, and once I know the orientation of the E vector, for example, if the E vector happens to be like this, then the S vector will be like this. So, it is just calculating from the given direction of the k vector, knowing that the d vector lies in the plane containing optic axis and the k vector, finding out the d vector direction, from the d vector direction get the E vector direction, and from the E vector direction get the S vector direction, because this is right angle. E and S are perpendicular, D and K are perpendicular. Okay, so, it is a small angle of 2.15 degrees or something like that, the angle between these two. So, this is what I had told you earlier, to check for the angle between the k vector and S vector. This angle is usually very small, a couple of degrees. Do you have any questions?
So, what is the maximum value of that psi minus theta means that?
What is the maximum value of this angle? This is what I asked you to calculate. It is a few degrees.
It's not 90 degrees.
No, because at 0 psi is equal to 0, E and D are parallel. At psi is equal to 90, they are again parallel, and in between there is a small angle, and that angle depends on this NO to NE ratio, because you remember the Ez by Ex was NO square by NE square into tan psi. So, the difference, the anisotropy is usually not very large. NO and NE are not very far from each other. So, this angular difference is usually very small, it is a couple of degrees, and the numbers which I gave you in the quiz, the psi was about 60 degrees, and so the angular difference is about 2 degrees or so only. It is a small angle. Anything else? Okay. Before we start discussion, I'll leave a problem to you. Please do this at home. So, remember these two equations we had written, dE 2 by dz is equal to I omega d by C n 2 E1 square e to the power minus I delta k z, and dE1 by dz is equal to I omega d by C n 1 E2 E1 star e to the power I delta k z. Show that these two equations satisfy energy conservation. E1 is the electric field of the omega wave, E2 is the electric field of the 2 omega wave, and so E2 is getting generated from E1, so there must be energy conservation. So, you need to show between these two coupled equations satisfy energy conservation. Okay, so I leave this problem to you. Okay, so what we have seen, we have actually solved this first equation under the assumption that E1 is almost a constant. This is also called no pump depletion approximation. The omega frequency, which is the strong wave which comes into the crystal, is called the pump, and you neglect the depletion of the pump. You neglect the depletion, you neglect the change in the power in the pump for low conversion efficiencies, and this is usually termed as no pump depletion approximation. And under this approximation, we solved this equation, and we found that for maximum efficiency, delta k must be 0, which we called as a phase matching condition. So, what we found is for maximum efficiency delta k is equal to 0. This implies k2 is equal to 2k1, which implies the refractive index at 2 omega must be equal to the refractive index at frequency omega. The electromagnetic wave at frequency omega and the electromagnetic wave at frequency 2 omega must be propagating at the same velocity. Now, that is not possible normally, because all media are dispersive. So, when you change frequencies, the refractive index will change. So, n 2 omega is larger than n omega. So, how do I satisfy this condition? Also, before we look at this problem, this is called the phase matching, and we discussed different interpretations of this. In the photon picture, as I said, the nonlinear medium is helping two photons at frequency omega merge into a single photon at frequency 2 omega, and phase matching condition is nothing but momentum conservation condition. So, we can draw what is called the vector diagram. So, here is the momentum vector of one of the photons, h cross k1, h cross k2, another h cross k1, and this is h cross k2. The sum of the two momentas are this length of the vector here, and this must be equal to the length of the h cross k2 vector. And they are all propagating in the same direction. So, all the vectors are, so this is my z axis, z direction. This is a very nice interpretation in terms of vector diagrams. We will use this vector diagram later again in other interaction processes. And so, if the sum of these two vectors is different from this length of this vector, then you do not have phase matching and your efficiency will drop down. So, we will come back to this vector diagram repeatedly when we look at the parametric processes also. Okay, so, this phase matching is an important issue. Let me look at this equation. Why there is this problem? What is leading to this problem? This problem is coming because of this term, exponential minus I k delta z, sorry, I delta k z. So, the equation which we solved is only this equation for 2 omega I omega t by c n 2 d, sorry, E 1 square e to the power minus I delta k z. When I integrated this equation, it is this term which is leading to the sinc function. So, if I make this disappear from this equation, if the equation did not have this term, then I will not have the sinc function and I will have increased efficiency. That means, the second harmonic will continuously grow as the wave propagates. So, there are two techniques, the two primary techniques. In one technique, I made delta k is equal to 0. That means, k2 is equal to k1, which means refractive index of the medium at 2 omega is equal to refractive index of the medium at omega. This I will use the birefringence of the crystal, and hence it is called the birefringence phase matching. Remember, in anisotropic media, there are two refractive indices. There are two waves, the ordinary wave and the extraordinary wave, and the extraordinary wave velocity or the refractive index as seen by the extraordinary wave depends on the angular propagation. So, it may be possible in anisotropic media to be able to achieve this condition by choosing the omega wave to be one polarization and 2 omega wave to be another polarization. I will show this, and so this is called birefringence phase matching. We will discuss this in more detail. The other technique is to introduce a z dependence of this nonlinear coefficient d. D is in our analysis assumed to be a constant. Suppose I modulate d along the propagation direction periodically. a periodic variation in D will have Fourier components, spatial Fourier components. I can use one of those spatial Fourier components to cancel this term. Fourier series will have sine and cosine series, sine and cosine, or an exponential, it is the same. So, I can actually use a periodic variation in the nonlinear coefficient to cancel this term. So, D will, if I choose a periodic value for periodic function of D, that periodic function will have Fourier components, and one of the spatial Fourier components can be used to cancel these effects of this, and that is the second technique called quasi phase matching, or called QPM. This is a very important technique, first proposed by Blumbergen in 1961, and the classic paper on nonlinear optics where he showed that it is possible to overcome this issue of phase mismatch through a periodic variation in the nonlinear coefficient. Okay, so first what we will do is we will look at Birefringence phase matching. So first we are looking at birefringence phase matching. Now remember, suppose I take a medium which is anisotropic. So there are the ordinary refractive index at frequency omega and the extraordinary refractive index at frequency omega. Then there is also an ordinary refractive index at 2 omega and an extraordinary refractive index at 2 omega. So if I look at a second harmonic generation of a 1 micron wave, so I will have refractive indices at of the medium, ordinary and extraordinary indices at the frequency corresponding to 1 micron wavelength, and the ordinary and extraordinary refractive indices corresponding to 0.5 micron wavelength. Now remember, because of dispersion, NO of 2 omega is greater than NO of omega, and NE of 2 omega is greater than NE of omega. As you increase the frequency, the refractive index increases. Now between NO and NE at one frequency, depending, there are kinds of positive and negative uniaxial crystals. So let me look at a negative uniaxial crystal in which NO is bigger than NE. So let me try to draw a figure, the index surfaces which I introduced in an earlier class. So let us draw the index surfaces. So I first draw the index surfaces corresponding to frequency omega. So I have the ordinary index surface corresponding to the ordinary wave and the extraordinary refractive index surface. So if NO is greater than NE at one frequency, the ellipse will lie inside the circle, touching the circle at this. So this is my z axis, this is x. So these two are at frequency omega. Now I want to draw in the same figure the index surfaces corresponding to 2 omega frequency. So because NO of 2 omega is more than NO of omega, the circle corresponding to the second harmonic wave will lie outside the circle. Now the ellipse. The ellipse may intersect this circle. That ellipse cannot intersect this ellipse, because that ellipse has to lie outside this ellipse, because NE of omega is less than NE of 2 omega. But that ellipse could intersect the circle or may not intersect the circle. So suppose I take a situation where the ellipse intersects the circle. So these are for 2 omega. So, under what condition will this intersect take place? Remember, this length is how much? This length is NE of 2 omega, and this length from here to here, the circle, is NO of omega. If this is less than NO of omega, then the ellipse corresponding to 2 omega will intersect the circle corresponding to omega frequency.
So that is NO of 2 omega.
NO of 2 omega is the circle here. NE of 2 omega is the ellipse. This is NO of omega. This circle is NO of omega circle, and this ellipse is NE of 2 omega ellipse. So, this length is the length corresponding to NE of 2 omega, this length is the length corresponding to NO of omega, and NE of 2 omega should be less than NO of omega for this ellipse to intersect the circle. When the ellipse intersects the circle, look at this direction. The ordinary refractive index at frequency to omega the ordinary index at frequency omega becomes equal to the extraordinary refractive index at 2 omega for that direction, some psi phase matching. So, this is some special angle. So, in such a situation, there are directions in which the ordinary refractive index at frequency omega becomes equal to the extraordinary refractive index at 2 omega along that direction. As I told you before, please differentiate between NE of 2 omega psi and NE of 2 omega. NE of 2 omega is a constant corresponding to NE of 2 omega 90 degrees. Okay. So, NE of 2 omega is the extraordinary refractive index as seen by a wave propagating perpendicular to the optic axis, the minimum value of refractive index as seen by the extraordinary wave for this crystal. If the extraordinary wave propagates in any other direction, the refractive index seen by the extraordinary wave will be more than NE of 2 omega for the 2 omega frequency. So, please differentiate between NE of 2 omega psi and NE of 2 omega. There is a formula for this refractive index which depends on the angle psi. So, there will be a special direction in which, along which the refractive index as seen by the ordinary wave at frequency to omega becomes equal to the refractive index as seen by the extraordinary wave at frequency 2 omega, and that I can obtain phase matching, that means. So, although there is dispersion, I am using the fact that there are ordinary and extraordinary refractive indices, and under this situation it is possible to achieve what is called as birefringence phase matching, because I am using the birefringence of the crystal to achieve phase matching. Now, what does this condition imply? Remember, 1 by NE square of 2 omega psi m will be equal to cos square psi m by NO square of 2 omega plus sin square psi m by NE square of 2 omega. Remember, we had obtained the refractive index as seen by the extraordinary wave when it propagates at an angle making an angle psi with the optic axis. For phase matching, this must be equal to 1 by NO square of omega, because my phase matching condition is this, and this implies that 1 by NE square of 2 omega psi m must be equal to 1 by NO square of omega. I can simplify this equation and I will get the following equation: sin square psi m is equal to 1 by NO square of omega minus 1 by NO square of 2 omega divided by 1 by NE square of 2 omega minus 1 by NO square of 2 omega. You just write the cosine in terms of sine, simplify this equation, and there is a specific angle at which, depending on the ordinary and extraordinary refractive indices of the crystal and depending on the dispersion in the crystal, it is possible to achieve birefringence phase matching. If Ne of 2 omega happens to be larger than No of omega, then the ellipse will lie outside the inner circle and there is no birefringence phase matching possible. So, birefringence phase matching requires anisotropy and certain relationships between dispersion and birefringence. Now, please note that if you deviate from this angle psi m slightly, delta k becomes finite, because No of omega, although No of omega remains the same, Ne of 2 omega will change as you change the angle. So, at this point it is very critical. The angle that you need to propagate the wave in is very critical. It is called critical phase matching. If this angle happens to be 90 degrees, then the circle, the inner circle will be tangential to the ellipse. So, it will look like this. So, I am just drawing the inner circle No of omega and Ne of 2 omega will look like this. So, I am not drawing the outer circle here and the inner ellipse. So, there is an inner ellipse here corresponding to omega frequency, there is an outer circle corresponding to the 2 omega frequency. So, sometimes it is possible that this angle psi m becomes 90 degrees. Sorry?
Then there will be no coupling.
Why?
The electric fields are mutually perpendicular.
No, there is coupling is brought about by nonlinearity. I will show you. Here also, even in this case, the two electric fields are orthogonal. One is ordinary wave and the other is extraordinary wave. So, the polarizations are perpendicular to each other, but there is still coupling because of the nonlinearity. Now, this is a very important issue, I will come to this. So, the same situation here, except that now it is possible that this angle becomes 90 degrees. In this case, look here, because the two curves are tangential, small deviations are not so critical. Even if you have a small angular mismatch, misalignment, you will not have a large delta k. Delta k is finite still, but it will not grow as fast as at this point when the two curves are actually intersecting. So, this is called critical phase matching, this is called non-critical phase matching. I am still using birefringence, but here the omega and 2 omega waves are both propagating perpendicular to the optic axis. One is an ordinary wave, the other is an extraordinary wave. So, the omega frequency is an ordinary wave, the 2 omega frequency is an extraordinary wave, but the two refractive indices. So, here is a situation where Ne of 2 omega becomes equal to No of omega. In this case, the phase matching angle is at 90 degrees to the optic axis, and because of the two curves being tangential to each other, small deviations in angle will not create a large delta k, and it is called non-critical phase matching. Now, it is possible in some situations to make this happen, because remember these refractive indices are also functions of temperature. So, I can use this equation and find out if it is possible to vary the temperature such that this psi m becomes 90 degrees. So, for example, if you take an element called, so if you take lithium niobate for example, it so happens that in lithium niobate LiNbO3, if your omega corresponds to a wavelength of lambda is equal to lambda 0 is equal to 1.1523 micrometers, at a temperature of 210 degrees Celsius, you can achieve non-critical phase matching, because it so happens that these values are such that psi m, the solution is 90 degrees. But this is not always possible. So, if you change the wavelength, then you are not able to satisfy this condition with psi m at 90 degrees. So, birefringence phase matching is interesting because you use birefringence, achieve phase matching, but you could have, if it is critical phase matching, you have to ensure that your propagation direction is according to this angle. So, let me give you an example. So, the first laser which was built was what? Ruby laser. What is the wavelength? .3. Red. Now, there is a crystal which is very popularly used, KDP. This is KH2PO4, potassium dihydrogen phosphate. It is a uniaxial crystal. It is transparent in the visible, and it is used in many second harmonic experiments. You can grow big crystals of this crystal, big size crystals. So, let me give you the numbers. So, corresponding to this wavelength, NO of omega is equal to 1.50502, NE of omega is equal to 1.46532, NO of 2 omega is equal to 1.53269, and NE of 2 omega is equal to 1.48711. Is it possible to achieve birefringence phase matching? The condition we needed was NE of 2 omega must be less than NO of omega. So, I can achieve birefringence phase matching. I substitute all these values in this equation and get the angle psi. So, psi m comes out to be about 50.5 degrees. So, if I take potassium dihydrogen phosphate crystal, propagate at an angle of 50.5 degrees with the optic axis and use this laser, I can satisfy the phase matching condition. But please note, in critical phase matching, the S vector of the extraordinary wave is not parallel to the K vector of the extraordinary wave. So, although the wave front is propagating at 50.5 degrees to the optic axis, the energy of the second harmonic is not propagating at that angle, it is propagating at an oblique angle. So, what will happen is the omega frequency wave will go along the same direction, but the 2 omega wave will deviate. The 2 omega gets generated and does not propagate along the z direction. The energy of the 2 omega is not propagating along the z direction, because the S vector of the second harmonic, which is an extraordinary wave, is not parallel to the K vector. So, this effect is called walk off, and this creates a problem in efficiency, because now they are no more interacting. If they separate out, they are not interacting anymore. So, you need to ensure that, so if you take a beam of a certain cross section, the walk off, that means complete beam walk off, will take place over a certain length depending on this angle. So, you can't use crystals much longer than that, because the omega wave is propagating like this, and the 2 omega wave starts from here, and then actually it is continuously feeding off at some other angle. So, this in critical phase matching there is another problem of beam walk off. In non-critical phase matching there is no problem, because you are propagating perpendicular to the optic axis. S vector of the extraordinary wave is parallel to the K vector of the extraordinary wave. Okay. So, it is always one always tries to find out the possibility of non-critical phase matching, but otherwise one has to use the critical phase matching issue and generate the second harmonic. So, this is an example of a crystal in which, so what is expected is, if I take a crystal, so here is my, suppose my KDP crystal, suppose the optic axis is like this. So, I propagate making an angle of 50.5 degrees with the optic axis. This is the frequency omega. And okay, tell me what is the polarization of the omega frequency with respect to this diagram? It is in the plane of the diagram or perpendicular to the plane of the diagram? Perpendicular to the plane. It is an ordinary wave, right? So, the omega frequency will come like this. This is the polarization state. And the extraordinary wave at 2 omega will get generated in a polarization parallel to this plane. Okay? So, this is the direction of k of omega, of k of 2 omega and s of omega. The Poynting vector corresponding to omega frequency, the propagation vector of the omega frequency, the propagation vector of the 2 omega frequency. But the Poynting vector of the 2 omega frequency is not parallel to the k vector of the 2 omega frequency. So, the energy that is getting generated at 2 omega is actually walking off from the beam, the main beam. So, here is a beam which is coming from here, and this polarization state, if I want to plot the d vector of the second harmonic, this is d of 2 omega. Remember, d vector is perpendicular to the k vector. So, when I say polarization in an anisotropic medium, it is the d vector direction. So, I launch a horizontally polarized light into the KDP crystal, and I am expecting the generation of 2 omega, which is in the plane of the in this vertical plane. Now, as he raised this issue, how am I sure that the second harmonic will generate it in the perpendicular polarization state? What is there to couple between this polarization and this polarization? Satisfying phase matching is one issue, but there must be a finite coupling. Suppose I take two pendulums which have an exactly identical time period, and if I make one oscillate, even if the second one is resonant with the first one, there is no energy transfer if there is no coupling. So, if I take two pendulums which are identical, even if I oscillate one of them, I must induce some coupling. I must put a spring in between or some mechanical object or something electromagnetic, so that energy, these two get coupled. So, first is this resonance. So, suppose I make a coupling and make them completely non-identical, again there is no transfer of energy. If I take two pendulums which are non-identical in length, and if there is a coupling, there is no energy transfer. There is coupling, but there is no energy transfer. So, two conditions are required. One is resonance and a finite coupling. So, resonance is something like here phase matching. The moment I satisfy phase matching condition, the transfer can be constructive all the time. But first of all, there has to be a transfer. There has to be generation of the normal perpendicular polarization state, and to analyze this, I must now go back and look at the complete equation, the vector equation for polarization in terms of the tensor components of D. Because with this analysis, it is not possible for me to explain or find out whether at all this is possible. So, to analyze this now, we move to the second aspect of this polarization, and that is we go back and look at this equation. Pi, remember Pi is equal to 2 epsilon 0 d I j k E j E k. This is the actual equation connecting the nonlinear polarization. This is only the nonlinear polarization. This is the ith component of nonlinear polarization, depends on the jth and kth components of the electric fields. I am not writing the summation sign. This repeated indices j and k are being summed over. Okay, so it essentially means, for example, Px nonlinear will be equal to 2 epsilon 0 into dx x x Ex square plus dx x y Ex Ey plus dx x z Ex Ez plus dx yx Ey Ex plus dx yy Ey square plus dx yz Ey Ez. How many terms will be there? plus dz x y sorry x x E x square plus dz x y x sorry x x x x x y x x z x y x x y y x y z then sorry yeah plus dx zx ex ez ex plus d etc. So many terms. Okay, how many? 9 terms, because these two indices can take 3 values each and I get 9 terms.
So what's the difference between dxyx and xxy?
There is no difference because they are both coefficients of this one and this one, they are the same. So these two elements will be equal. That means the latter two indices can be interchanged without changing the value of the coefficient. So which means that dx xy will be equal to dx yx, because both are coefficients of ex ey.
But aren't we adding them twice then?
Yeah, so I will have two times factor here.
Okay.
So these two are equal. See, when a plus b whole square I will get 2ab, right. So similarly I will get 2 times. So this is, please remember here also that these are total electric fields and this is the total nonlinear polarization. This will contain omega, 2 omega, 3 omega, whatever it is, all kinds of frequencies. So this equation relates the total polarization to the total electric field. Now let us apply this to, so this is the general equation relating the nonlinear polarization to the electric fields because of second order effect. This is a second order nonlinearity because there is the product of 2 electric fields. In the third order I will have chi I j k l E j E k E l. Okay. So this d I j k has 27 elements and I can't write this matrix because it's a 3 by 3 by 3 matrix, it is a 3 dimensional matrix. Okay. But as erased, fortunately there is no difference between E j E k and E k E j. So d I j k is equal to d I k j, and that will help me in what is called as contracting indices, and I can transform this into a 2 dimensional matrix. I will show you. Okay. So before that let us look at what kind of nonlinear polarization will I generate at 2 omega frequency. So for this now I must worry about the components of electric vector. So let me write E j is a sum of jth component of omega electric field and jth component of 2 omega electric field. Okay. So I will have half E j of omega e to the power I k 1 z minus omega t plus complex conjugate plus half E j of 2 omega e to the power I k 2 z minus 2 omega t plus complex conjugate. Similarly, the kth component of electric field will be simply this with j replaced by k, because I do not know a priori what are the components of the electric field of the wave at frequency omega and the frequency 2 omega. Plus complex conjugate. So I need to substitute this into this equation 2 epsilon 0 d I j k E j E k. E j superscript omega is the jth component of electric field at frequency omega. This is the jth component of electric field at 2 omega, kth component of electric field at omega, kth component of electric field at 2 omega. Okay. Now can you tell me when I, so I must multiply these two, then multiply by 2 epsilon 0 d I j k and find out p I at 2 omega. So what will I get? So, first thing is I get 2 epsilon 0 d I j k, and half into half is 1 by 4. Now, tell me what terms will I get when I multiply these two at frequency 2 omega. This into this will give me 2 omega. This complex conjugate into the complex conjugate will also give me 2 omega, that is the complex conjugate. Anything else? There is no other term. So, I will have here E j omega, E k omega, exponential 2 I k 1 z minus omega t plus complex conjugate, which I can write as follows. P I of 2 omega is equal to half of epsilon 0 d I j k E j of omega E k of omega exponential 2 I k 1 z minus omega t plus complex conjugate. So, this expression is exactly like the electric field, half of a component plus its complex conjugate. Just like I wrote before, P nonlinear at 2 omega as half of something into exponential this thing plus complex conjugate. Remember, we had obtained E square earlier, epsilon 0 d E square we had got. Now, E square is actually E j omega E k omega. So, let me call this as half of P I tilde at 2 omega exponential 2 I k 1 z minus omega t plus complex conjugate, where P I tilde at 2 omega is equal to epsilon 0 d I j k E j of omega E k of omega. Please differentiate between this equation and this equation. This is the total nonlinear polarization. There is 2 epsilon 0 d I j k E j E k. This is the total electric field. This is the total nonlinear polarization. This equation here gives me the ith component of nonlinear polarization at frequency 2 omega because of the jth and kth components of the electric fields at omega. This electric fields contain both omega and 2 omega. These electric fields are only at omega. Now, I leave it to you to find out a similar expression for P I nonlinear at omega, because when you take a product of these terms, when you multiply those electric fields, when you multiply this E j E k here, when you substitute and multiply from these products, you will also get terms of the type exponential minus I omega t. So, please pick up those terms and next time tell me what their equation is. So, P I nonlinear at omega I want to find out. So, I will have to write it in this form, half of something into exponential I, you will get k 2 minus k 1 into z minus omega t plus complex conjugate, exactly like before, except that now this is the component form. Earlier we did not worry about the components of electric vectors and so on, but here this is now the actual ith component of nonlinear polarization at second harmonic generated by the jth and kth components of electric fields at omega frequency. So, let me look at an example. So, first thing is, as I told you, j and k indices can be interchanged because there is no difference between E j E k and E k E j. So, I can actually contract these two indices. So, there is a particular standard convention for contraction. 2 indices 1 1 is represented by 1, 2 2 is represented by 2, 3 3 is represented by 3, 2 3 3 2 is represented by 4, 1 3 3 1 is represented by 5, and 1 2 2 1 is represented by 6. You can remember very easily, this is 1 1 2 2 3 3 2 3 1 3 and 1 2. So, this is 1 2, 3, 4, 5, 6. This is a standard convention used to describe piezoelectric tensors or electro-optic tensors or nonlinear optical tensors and so on. Whenever indices are contracted, this is a standard notation. So, when I say D14, it means I is 1 and the second coefficient is 4, that means it is either 2, 3 or 3, 2, both are same. So, D123 is D14, D112 is D16 and so on. So, the last two indices are contracted, and so when you contract this now, D tensor becomes, what is the dimension of the matrix? 3 cross 6. Okay. So, I can write the D matrix like this. So, D tensor will be D11, D21, D31, D11, D12, D13, D14, D15, D16, D22, D23, D24, D25, D26, D32, 33, D34, D35 and D36. 18 elements instead of 27. Now, if you know the symmetry properties of the crystal, that symmetry property must be exhibited in the properties of the medium. So, if I can actually use the symmetry properties present in a crystal to find out which of these elements are 0, which of these elements are equal to each other, which of these elements are negative of each other and so on. So, I apply symmetry operations on I know the symmetry properties of my crystal. If there is a mirror symmetry, that must be exhibited here. If there is a rotational symmetry by 90 degrees, that must be exhibited here. So, any symmetry will be exhibited here. So, actually I can for a medium I can find out which elements are 0, which elements are non-zero, which elements are equal to each other and so on. So, all crystals belonging to one class will have the same D matrix. The values may be different. So, let me give you for KDP, potassium dihydrogen phosphate 0, 0, 0, there are only 3 non-zero elements. Okay. And similarly for lithium niobate there is another matrix. All crystals belonging to the KDP class, ammonium dihydrogen phosphate is another crystal which is like KDP, it has the same matrix except that the values for these coefficients may be different. And as I told you, these are typically 10 to the minus 12 meters per volt, the values. Okay, so because of this contraction, my equation actually is this equation which I wrote down earlier, simplifies to P I tilde of 2 omega is equal to epsilon 0 d I j d I, okay, no, let me write like this, sorry. Okay, so let me write the P x tilde of 2 omega will be, now you see whenever j and k are equal, sorry, whenever j and jk and kj terms are there, they are equal. So, what will I get when I expand? I will have epsilon 0 dx xx ex square ex at omega square actually plus epsilon 0 dx yy ey of omega square plus epsilon 0 dx zz Ez of omega square plus, now I will have dx xy dx yx and similarly, so I will have 2 dx yz ey ez plus 2 dx xz Ex of omega Ez of omega plus 2 dx xy Ex of omega to Ey of omega. There are still 9 terms. Actually, these 3 terms contain twice the number. Similarly, I can write an equation for Py of 2 omega, Py tilde, Pz tilde. So, actually you can write this entire thing in a matrix equation, Px tilde of 2 omega, Py tilde of 2 omega, Pz tilde of 2 omega is equal to this D matrix. So, D11, D12 etc. into Ex of omega square, Ey of omega square, Ez of omega square, 2 Ey of omega, Ez of omega, 2 Ex of omega, Ez of omega, and 2 Ey of Ex of omega, Ey of omega. For example, I can check this. So, Px tilde of omega, so d11 Ex square, d12 Ey square, this is d12 plus d13 Ez square, this is d13, this is 2 d14 Ey Ez. So, this d14 multiplied by 2 Ey Ez. Then I have 2 d15 Ex Ez. So, 2 d15 Ex Ez and 2 d16 Ex Ey, 2 d16 Ex Ey. So, the 3 components of nonlinear polarization that are generated are related to the electric fields components at frequency omega, the x and y and z components through this matrix relationship. So, what I will do in the next class is look at some examples KDP and lithium niobate, and as I gave you this example 50.5 degrees I need to travel at perpendicular at making an angle of 50.5 with the optic axis, but 50.5 can be in this cone. Is there any restriction? I will show you that if you are not careful, you may have no coupling. You will be phase matched, but there is no coupling because the nonlinear coefficient for that interaction may be 0. So, you need to be careful in not only achieving a phase matching, but also choosing the right direction with respect to the crystal axis, so such that there is a finite coupling between the omega and 2 omega frequencies. Okay. Are there any questions? Yes.
While we were deriving the equation for the eigenmodes for the extraordinary and ordinary ray, there we did not have these terms, nonlinear terms where the Ex was affecting the polarization y direction, z direction.
No, that is anisotropic medium under linear approximation. We were studying the linear properties of anisotropic media.
But we use that result here.
Yeah, because actually the nonlinear, what is nonlinearity doing? It is nonlinearity is generating or coupling different frequencies. So, once an electromagnetic wave gets generated at the new frequency, it will propagate through the medium as per the Maxwell's equation which we have solved. So, all that the nonlinearity is doing is generating a nonlinear polarization which acts as a source to generate electromagnetic waves at the new frequency, and that wave will travel just like a wave in an anisotropic medium, which we have analyzed earlier.
So, it's perfectly alright to use those results here, or is it an approximation?
No, it's perfectly all right. It's perfectly all right. It is like I can analyze the problem of a pendulum individually, and when I have coupling, I still use the same set of equations with an extra coupling in between and say that there is energy transfer, etc. So, there is no problem at all. No. Anything else?
This would lead to a 4 omega generation also, because the second harmonic generation will again, while traveling in the anisotropic medium, will have a 4 omega generation because of
Nonlinearity. Yes. Now, will 2 omega generation will also lead to 4 omega generation? Yes, in principle, but I need to satisfy the phase matching condition that the refractive index at 2 omega must be equal to the refractive index at 4 omega. So, which in general will not happen. So, I will not be number 1. Number 2, the power generated at 2 omega is already very small. So, that at that frequency there is no nonlinearity. This, I mean, the nonlinearity is very weak, corresponding to 2 omega to 4 omega conversion. So, in general that does not happen, but it is always possible to have a situation where that is also being satisfied, and then I have to solve that equation also simultaneously with this. Okay, thank you very much.